Okay, folks, picking up where we left off from the mean free path and collisional frequency, let's take that and develop it a little bit further and think about how we can come up with a fundamental way of deriving a rate constant and a reaction rate from this whole notion of collisions, from collision theory. So we can think of this as, either A plus B makes products or A plus A makes products, right? And then noting in this second, both of these are second order reactions, right? So my dA by dt would be negative K times A times B, so all of that still applies, or dA by dt is going to equal negative Ka squared. So if we try to develop some kind of rate fundamentally, we know that they need to take on the same units, right? And our units of our reaction rate is going to be molecules per, I'm going to keep that in our standard gas phase unit, cubic centimeter per second. So that will be the unit of our rate. And the unit of our rate constant, right, will be, so let's see if I left myself enough room. So the unit of our rate constant there for second order will be cubic centimeter per molecule per second. Okay. So now, if we think about how to build this up fundamentally, a rate constant should be proportional to the following things. So the frequency of collisions, as we just described, so Z equals sigma times C bar relative times our number density. So N, recall, we made that equivalent to P over KBT. There's also going to be some minimum energy requirement given by the Boltzmann distribution. And we can write that as E to the negative EA divided by KBT, where EA represents the minimum threshold energy needed for reaction. And this whole now Boltzmann expression states that there will only be some fraction of molecules that possess that minimum threshold energy for reaction. And then finally, there's this steric factor related to the orientation. And that typically gets the letter P. And so that means, not all collisions are effective. Some collisions need to be in the exact right orientation to go on and lead to a reaction. So now I'll start by writing capital Z AB and noting that we need this to be a reaction rate. So let's start by putting that all together. So we know we're going to have this orientation factor, P. We know there's going to be some frequency of collisions, sigma times C bar relative. Let me make sure I write that down nicely. Sigma times C bar relative. I'm going to leave the number density alone for just a minute, and you'll see why, hopefully. And then now we've got this minimum energy requirement, E to the negative EA over KBT. And now with respect to my number density, we really need the number density of both things. So in that previous derivation, we only included the number density of one. We put one molecule in our collisional tube. In reality, if we want a reaction out of this thing, we need two molecules in that collisional tube. So we need the number density of A and we need the number density of B. So now if we start playing around with this and seeing what kind of units we get, let's first look at this chunk right here. So P will be unitless. Sigma will take on units. We'll keep everything in the centimeters. So that'll take on units of centimeters squared per molecule, even though we noted in that previous video we had units that were square nanometer per molecule. Relative velocity, we know typically we put that in terms of meters per second, but we'll keep it in the centimeter unit. So we'll write that as a centimeter per second. And then we know this E business is going to be unitless. Well, if you look at this right here, that gives us cubic centimeter per molecule per second. So that means all of this stuff is equivalent to our rate constant. Okay, so now what about these things? Well, each one of these will have units of molecule per cubic centimeter and molecule per cubic centimeter. So now if we continue to combine all of these units, right, the molecule per cubic centimeter cancels with this molecule per cubic centimeter, but then this one will survive. So what we're left with is a molecule per cubic centimeter per second. So lo and behold, there we have it. We have a fundamental way of coming up with what a rate law is without using any of this kinetic stuff. So let's keep going with that. So now we can write that the rate constant K is going to be equal to the following. So we still have that orientation factor, P, times sigma. Now I'll include the equation for C relative, 8 kBt over pi times mu, all square root, and then e to the negative EA over RT. So as you might guess now, what all of this becomes is our Arrhenius frequency factor. Thus, right, we have derived the Arrhenius equation from fundamental principles. So, oops, I wrote RT right there. Let's be consistent and just note that if I have KBT over here, I should keep KBT over here. And of course, we could do some unit conversions and get that in terms of R. So now let's talk about this collisional, or this steric factor, rather, this orientation business. Okay, so we can think of it very much like the way we talked about our cross section, where we're going to have some actual area the molecule exists in. So sigma would be its physical cross section. So, you know, the actual geometry of the molecule. And sigma star is the reactive cross section. So that means P is my steric factor, and it literally just is some unitless orientation parameter, right? It's unitless. It basically scales sigma down to sigma star based on what we know about the molecule. So for example, if we were thinking about OH reacting with a double bond in some organic molecule, right? We know that this is the size of the molecule, sigma, but the OH radical, right, it attacks the double bond, so we know that that is really the true reactive cross-section. And so when we go to measure the frequency factor in a real experiment, right, so if we go natural log of K versus 1 over T, we know that the intercept of that line will give us the frequency factor. And the slope, of course, negative slope, will be equal to EA over R. So if we do this for a real experiment, that steric factor will inherently be a part of our experiment. We've got no way of teasing that out. However, it's really difficult to calculate what P is fundamentally. So if we only attempt to calculate A just based on our thermodynamics, right, like not including that steric factor, then our A will be apparently fast. It will look like it's reacting too fast because generally that steric factor is less than 1, but not always. So there's some fantastic examples where the steric factor can actually be greater than 1, typically with ionic reactions. So if we don't include that steric factor, it looks like our reactions will be occurring faster than what they actually are. Okay? All right, so we'll play with these equations a little bit more in our live lecture. I'll see you then.